Okay, since last time we did this thing, we were calculating the binding energy and the mass effect of different elements, and we did this example like carbon, uranium, and lanthanum, and I gave you these examples to do on your own. Let me do one more question for you to revise the previous lecture, right? Okay, so the mass of the molybdenum nucleus is given, that is 94.945 U, right? And how many protons are there? 42. How many neutrons are there? 95 minus 42, right? So you can see that 95 minus 42 is 53 neutrons, right? And 42 protons. Okay, so if we want to calculate the mass of the nucleons, then it's gonna be, let's say this, and this is going to be 42 times 1.007, which was the mass of one proton, plus 53 times 1.009, which is the mass of one neutron. So if we do it, so this mass is since 95.771 U, right? So this is the mass of the nucleons. And now if you want to like, and the mass of the nucleus is this, right? And now if we want to calculate the mass effect, then it would be this delta M equals to capital M minus M, and that is like 95.771 U minus 94.945 U. So we can calculate it. So since it is 0.826 U, 0.826 U. So this is the mass effect of molybdenum nucleus. And we can also calculate it in kgs, 0.826 times 1.66 times 10 to the power negative 27, right? So we can see that what's going to be the answer. Sister's answer is going to be 1.37 times 10 to the power negative 27 kg. So this is the mass effect of the molybdenum nucleus. And if we want to calculate the binding energy, then it's going to be this delta E, which is equals to delta M times C square, right? C is speed of light. So mass is 1.37 times 10 to the power negative 27 times speed of light is 3 times 10 to the power 8 whole square. So we can have a look at this thing, that it's going to be this thing. Delta E is going to be 1.23 times 10 to the power negative 10 joules, right, students? So I told you we can also convert it into like million electron volts. So this is basically delta E. We are going to call it total binding energy. Total binding energy is going to be 1.23 times 10 to the power negative 10 joule. And if we want to convert it into like million electron volts, and then we can divide it by the number 1.6 times 10 to the power negative 30. Right, so 1.6 times 10 to the power negative 13, then it's going to be 771 million electron volts. Right, students? But do remember that this is the total binding energy. If you want to calculate the binding energy per nucleon, then it's going to be this. We represent it by B, capital B, subscript E. So that is the binding energy per nucleon. Binding energy per nucleon, right? So how many nucleons are there in molybdenum? You can have a look at the first line, which is 95. So we are gonna, put the value of the total binding energy, 771 million electron volts, and we are gonna divide it by the total number of nucleons. So it's gonna be 95, and that is, it's gonna be 8.11 million electron volts. That is the binding energy per nucleon for the molybdenum nucleus. So these are all the questions that the examiner asks about this topic. So you can repeat this whole thing for nitrogen, and then you can do this for oxygen as well, right? There is a question here. We have to do the controlled reaction between the deuterium and tritium has involved ongoing research for many years. The reaction is summarized by this. And the question is, you're also given that this is the Q. Now, what is Q? Q is written here at the right side of the equation of the nuclear reaction. So the value of the Q is telling us that it is the energy released, right, students? So this is the energy released, right, students? So, and you can have a look from the reaction that what's going to be the type of the reaction. It is actually this deuterium and tritium. They were like smaller nuclei, and when they combined together, they formed a heavy nucleus, right? So this is basically nuclear fusion, right, students? So fusion reaction. I'm telling you just for the information, we're going to study fusion in detail in the upcoming lecture. Okay, now binding energy per nucleon for hydrogen is given, helium is given, but for neutron it is not given. So that's what the examiner asks as well. That suggests why the binding energy per nucleon for the neutron is not quoted. So I've already told you this thing in the previous lecture that the binding energy for a single nucleon is not defined. So you'll be saying neutron is a single nucleon. So binding energy per nucleon is not defined. Right, students? Okay, so what I'm calling as binding energy per nucleon, I'm calling this symbol as binding energy per nucleon, right? Okay, so let's go further. Okay, so next is this. Yes, we know that the mass number, what is a mass number? We have been studying it since our O levels, right? So mass number is the sum of the all nucleons or the protons and neutrons all together, right? Inside the nucleus, definitely. And what is nuclear mass? It is the mass of the nucleus, and it is definitely measured in U. So these two things are entirely different, mass number and nuclear mass. Remember that, right? For example is like mass of the uranium nucleus 235, mass number is 235, right? But its nuclear mass is 235.123 U. So this is mass number and this is nuclear mass. Remember, there is a clear difference between them, right? Okay. So difference between the mass number and the nuclear mass, there is always a difference in two numbers, that is the mass number of the nucleus and nuclear mass, except carbon atom. For carbon atom, they are entirely equal, whose nuclear mass is 12, as well as the mass number is also 12, right? So this was a very important information because the next topic depends on it, mass excess. Okay, so mass excess basically defines the difference between these two. The difference between the nuclear mass that we calculated and the mass number of that nucleus is called mass excess, right? So mass excess is defined as nuclear mass minus the mass number, right? And there are three types of the mass excesses. First is positive mass excess, second is negative mass excess, and then the zero mass excess, right? So let's talk about some positive mass excess, like if we talk about, yes, this example, uranium. Uranium nucleus mass is this, 235.123, while its mass number is 235. So the mass excess would be 235 0.123 minus 235. So that is 0.123. So this is the positive mass excess because it is positive in number, right? So how do we define then positive mass excess? It is when the nuclear mass is greater than the mass number, right? Okay, so there is a negative mass excess as well, and that is going to be definitely opposite to that when the nuclear mass is less than the mass number. And the example for that we have is potassium, right? Potassium's mass is this 39.0983, and its mass number is 40. So mass excess is going to be 39.0983 minus 40. So it's going to be a negative number, right? So that's why we call it negative mass excess. And we can also talk about the zero mass excess. Zero mass excess is going to be when the nuclear mass is going to be equal to the mass number, right? For example, if we talk about carbon, its mass is 12.000 U and its mass number is also 12. So if we take the difference of them, then 12 minus 12, it is zero mass excess. That's why we have made carbon the reference atom to define the relative atomic mass, right? Now you have done it in your chemistry. Okay. Now let's talk about some nuclear reactions. In any nuclear reaction, if let's say we have these elements, X and Y, the parent nuclei, and they give us the A plus B, which are the daughter nuclei, right? And then X and Y are called what? Parent nuclei, and A and B are called what? They are called the daughter nuclei, right? Okay, E1 is the energy absorbed and E2 is the energy released in the nuclear reaction. In both types of the nuclear reaction, fission and fusion, E2 is always greater than E1. So you must remember that E2 is always greater than E1. So overall reaction is always energy released. So So it means okay, if we like talk about the difference of E2 and E1 and we write it as like E2 minus E1 equals to E, then that energy is always released. So the newer simplified equation must be looking like this, shaded in light blue color, right? Where E is the total energy released in this reaction. Okay, so now here is a question. The question is, when the uranium absorbs slow-moving neutron, one possible nuclear reaction is this, right? So here is the uranium, molybdenum is formed, lanthanum is formed, and then two neutrons are released and seven beta particles are also released. Along with one more thing, and that is what? Emission of energy, right? So this is the energy which is released, okay? So now these things are given, this data will always be given. Like I have been using these values in the previous questions. You have seen this thing, right? Okay, so the question is calculate the total mass effect of the above reaction. Yes. So one was the mass effect of the element. This is the mass effect of the reaction, right? So what are we going to do? We're going to simply subtract the mass of the daughter nuclei from, oh, sorry, mass of the parent nuclei from the mass of the daughter nuclei. Now, what are the daughter nuclei? Daughter nuclei are seven beta particles, two neutrons, one lanthanum nucleus, and one is molybdenum, right? So let me sum them up for all. So it's gonna be looking like this. Yeah, so seven beta particles are gonna be this. Seven times mass of one beta particle is this, given in the table, first option, right? So 7 times 5.5 times 10 to the power negative 4. All masses are given in U. Plus 2 neutrons. 2 times 1.009. Plus lanthanum. Lanthanum nucleus is given in the last from the table. So its mass is given 138.955, right? and then plus the mass of the molybdenum nucleus, which is the second last entry here. So it is like 94.945. So, right, so this is the whole mass of the daughter nuclei. And then we have to subtract what the parent nuclear mass, which is like first uranium. Uranium is given in the table here. So it's going to be 235.123 plus one neutron, that is 1.009. So you can calculate this thing, right? So the answer is 1.85 U, right, students? So this is the total mass defect of the reaction, right? Let me write it. This is the mass defect of the reaction. Mass defect of the reaction. And now if we want to calculate the total energy released in the reaction, energy released in the reaction, then we are going to use this mass and apply Einstein's mass energy relationship, right? So it's going to be looking like what? Delta E is equal to delta M times C squared. The mass will be converted into kgs, 1.85 times 1.66 times 10 to the power negative 27 times the speed of light is 3 into 10 to the power 8 whole square, right? So let me do it. Okay, students, there is a mistake in the previous calculation. This number is wrong. Rather, it is what it is point. It is wrong. So answer is 0.212. Right. So here I'm gonna replace 0.212. Right. So then we can convert it into kgs, and then we can multiply it by the square of the speed of light. So since this is the energy released in the reaction, that is 316 times 3.16 times 10 to the power negative 11 joules. And we can convert it into like million electron volts by dividing by the same conversion factor. So what is it? Is this 198 million electron volts? Yes, this is correct. Right. Okay. So the next question is this: one possible reaction for this, the helium and nitrogen combining together to form oxygen is this. Calculate the mass effect of this reaction. Again, you can do the same procedure as we done previously, right? Okay. So now we have this question. When uranium absorbs a slow-moving neutron, one possible nuclear reaction is this. Calculate the total mass effect, which we just did in the previous part, and then calculate the energy release. I told you 198 million electron volts. We just calculated it, right? So it's the same question. Okay. Okay, again, the total mass effect, you can do it for this and the total energy equivalence, right? And if you are asked to explain whether that energy is released or absorbed in the reaction, sorry, this is not the portion of the exam. I wrote this question myself. This is not asked in A-levels, right? Yes, this question is going to be asked. Using your above answers, explain that for the above reaction to start, helium and near nitrogen must move with some velocity. Yes, definitely, because both are nuclei, so both will be repelling one another. So to overcome the repulsion between the nuclei, between the nuclei, right, students? They must be moved with some velocity, right? Okay. So again, we have this question. We are given the same reaction. We are asked to calculate the total mass effect. Oh, it's the repeating question, right? The same question is being repeated. Okay. Yes. Let's do this question. Question is when a neutron is captured by a uranium nucleus, the outcome may be represented by this equation. Use the equation to determine the value of x. This is x and the reaction. So students, we know okay the atomic numbers and mass numbers must be same at both sides. So let's write them down at the left side, which is like 235 and 1. So 235 plus 1 is going to be, what about the right side? 95 plus 139. 95 plus 139 plus x, because this x into 1x plus 7 times 0, right? So we can calculate it that it's going to be 236 minus 95 minus 139. So since we can calculate the x and it's going to be 2, so we're going to write here 2. State the name of the particle represented by this. So this is the beta particle, right? Okay, you know that. Okay, so now the question is a little different. Like we are given the elements, actually elemental nuclei, right? Their mass in U and the binding energy per nucleon, right? For the above reaction. Here is the reaction, right? Okay. So the question is determine the binding energy of the uranium nucleus. You know that. How to do it? We are going to first calculate the mass effect. Mass effect is going to be delta M, and it's going to be the total mass of the nucleon, that is 92 times 1.007 plus how many neutrons are there? 143, I think, yes, times 1.009 minus the mass of the nucleus, which is 235.123. So we've already done it. I just did it for you for your revision. Okay, so let me do it again. Yes, 235 minus 92. So yes, so it is 1.808 U, right? 808 U. So they asked us to calculate this thing in U. So this whole thing is for 3 marks, right? The next question is show that the binding energy per nucleon of the uranium nucleus is this. So first of all, let's calculate the total binding energy. Delta E as total binding energy from the Einstein's mass energy relationship, which is delta M times C squared. Delta M will be definitely converted into U. So we are going to convert this, multiply this number by this conversion factor, and then we're going to multiply it with this square of the speed of light. So if we do it, then it's going to be this thing. Yes, so it is 2.7 times 10 to the power negative 10 joules. And if we convert it into million electron volts, then it's going to be, yes, divided by this number, this, right? So if we do it, then it's going to be this. So since it is 1688 million electron volts. So this is the total binding energy, right? Total binding energy. Now the binding energy per nucleon, which I told you, is going to be total binding energy divided by the total number of nucleons. So that is what 1688, and what are the now total number of nucleons in the uranium 235. And if you do it, then definitely you're getting 7.18 million electron volts, which is asked in the question here. You can check this calculation, right, students? The kinetic energy of the neutron before the reaction is negligible, used to calculate the total energy released in this reaction. So now we are gonna do something else, and that is what? Yes. So we have to calculate the total energy released in the reaction. And now we know the binding energy per nucleon for uranium is like this. That's 7.18, right? So we can do it like by saying that total energy released, total energy released of this reaction. Its formula is the total binding energy of the daughter nuclei, right, minus total binding energy of the parent nuclei, right, students? So let's talk about the daughter nuclei. Daughter nuclei are these. The binding energy per nucleon is, students, 8.09 for molybdenum, and the nucleons are 95. So 95 times 8.09. 95 times 8.09 plus. Now let's talk about lanthanum. It is 7.92 times 139. 7.92, 139. 7.92 times 139, right? That is the total binding energy of the daughter nuclei minus the total binding energy of the parent nucleus, and that is 7.18 times the nucleons are 235. So if we calculate it, since then we are going to get uh, yes, so we're going to get 95 times 8.09 plus 7.92 times 139. So since we're going to get 181 million electron volts, right? So if the answer is negative, then you can do the try this. Like instead of total binding energy of the daughter minus parent, you can do total binding energy of the parent minus total binding energy of the daughter. Then you're going to get this number as positive, right, students?